see so many of you here, and also welcome to anyone who will be catching us later on YouTube. We know there are a couple of other meetings on today, but a great turnout. For those of you who don't know me, I'm Claudia Pagliari. I convene the eHealth Interdisciplinary Research Group here in Edinburgh and the Master's Programme in Global eHealth. And it's my great pleasure today to welcome Professor Peter Diggle here to give our latest Global eHealth seminar, also part of our public health research series. I was very intrigued when I heard or saw a snippet of Peter's presentation on statistical methods in eHealth some time ago, having worked on a number of eHealth evaluation projects, data linkage projects, trials, other types of projects in which the complexities of eHealth and the challenges of doing statistical research in eHealth were apparent. And I was hoping for the grand solution in the form of this seminar here. And I had a good look at Peter's profile on the web. And first of all, I was very comforted to see that he's a graduate of the University of Edinburgh, having taken his first degree in mathematics in the Appleton Tower, when it's all shiny and new, unlike it is today, all the bits falling off it. But undergoing refurbishment shortly, I'm told. He then moved on to post in a number of other universities, including the University of Oxford, and he's held posts in Australia. He's got fellowships in Johns Hopkins in the UK, in the USA, and so forth. And he now has a joint appointment with the University of Lancaster and the University of Liverpool. Now, Peter's very interesting in the sense that he's combined a long-standing interest in computer science and mathematics with the study of population health. He's represented on a Centre for Patient Safety Research, for example. He's working in tropical disease medicine. In fact, I downloaded a YouTube video on what statistics can tell us about tropical disease epidemiology not that long ago. Very interesting. He's worked on all sorts of different areas and really represents an interdisciplinary scientist of the type that we encourage in this network. So without further ado, I'm going to hand over now to our distinguished speaker. I should say one more thing. He's been elected and is currently in the position of President of the Royal Statistical Society. So again, a great sort of high five to the Statistical Society for electing a truly interdisciplinary scientist. And I'll pass you over now.
Thank you, Claudia, and thanks for the invitation. This is a bit of a kind of a tour of a range of problems, starting with something that's both complete and very simple, and finishing up with things which are in various states of incompleteness. And what I should acknowledge straight away, and I don't need to tell this audience, is that if you ask the question, what is eHealth, then depending on who you ask, you'll get very different answers. And I think it's fair to say that the network of eHealth research centres recently established by MRC, one of which is based here-ish, not in this building, but here-ish, one of which is in the northwest, which is where I work, one in, I think, London and one in Wales. I think although they're all badged as eHealth research centres, what they actually do is really quite different. And the interesting thing will be, when we eventually all get together, whether we can really do some cross-fertilisation, not just between the disciplines within our respective institutions, but across the network as a whole. Having offered the lazy student's answer to it on my next slide, which is to go to Wikipedia, I'll talk about the kind of statistical tools that seem to me to be likely to prove most useful in eHealth research, arguing in particular that randomized trials, beautiful though they are not going to cut it for a lot of the kind of eHealth database problems we encounter. And mainly the talk is a series of case studies, which I hope will end with a bit of a general message of a way forward. I can pause for a minute if you guys want to get some more comfy seats. There's several spare at the front. Okay, so here's the lazy student and indeed the lazy professor's answer to what is eHealth from the Wikipedia encyclopedia. It's hard to disagree with any of those words. It's just that you could have written a lot of different words as well. And what is perhaps more pertinent to how I got involved and how the network of eHealth research centres was formed in the UK is the MRC call. The focus there being to assess risks to public health, which is the kind of thing I kind of do. So that allowed me to get involved. The question is, if you want to do eHealth research with a view to understanding risks to public health, what kind of tools do you need? And you need data, right? So you need access to electronic health records and linkage of those health records with other relevant variables. And in the UK setting, we can imagine that we want to look at socioeconomic records, which we can access in principle from the census. There's an increasing amount of geospatial information accessible electronically on the physical environment that we live in, and things like real-time weather updating data and all that sort of stuff. And also there are increasingly a pressure, I think a perfectly reasonable one, for publicly funded researchers to make their data accessible more widely. And so a lot of the... Is that not working? No? Do you want it... maybe I should have plugged... Okay, it's only for him, fine. But can you hear me at the back? No worries, good. Okay, what about the methodological tools? Well, of course, the thing that lets me in is that it seems to me that there are statistics and computer science are key disciplines, and I'm a statistician primarily. Certainly, that's the only thing I've been trained in. And I never quite know what informatics is, but I think of it as some kind of blend of statistics, computer science, and subject matter science. And it's worth mentioning in this context that, of course, the buzzword bioinformatics these days tends to have a very molecular flavour, and health informatics has more of a population flavour. And certainly what I'm interested in is health informatics, not particularly bioinformatics. So all the geneticists can leave the room now and I won't be offended. Right. Now, if we're going to do statistics for eHealth data, then what kind of statistics do we need? Now, within our own eHealth centre in the northwest of England, there is a programme in clinical trials methodology, and quite right too. I'm not going to downplay the importance of clinical trials in public health research, just as in pharmaceutical research. But in terms of the kind of innovative statistical methodology that we need, I think the focus in eHealth research is bound to be very much on observational data. And in particular, a lot of the data that we can now access electronically is referenced both in time and in geographical space. And usually both of those dimensions are relevant to understanding the phenomenon that we're dealing with. A lot of public health issues have an obvious seasonal pattern. Some public health issues have emerging trends, which you'd really like to know about sooner rather than later, of which Ebola is a spectacular example at the moment. And for different reasons, in both developed and developing country settings, where you live is a reasonable predictor of the kind of health outcomes you can expect. Certainly a partial predictor, and worth understanding the nature of that geographical variation in relation to health outcomes. The other thing that electronically recorded data ought to imply is real-time analysis. And without replacing carefully designed and executed and reported studies that take place on a time scale of years, if you've got data being generated in real time, there must be a place for at least some form of real-time analysis to filter that data, so that you can begin to focus people's attentions on the important parts of the data. And the way I sometimes actually sort of articulate this recently is that for about 100 years, statisticians have been occupied in trying to get the best possible, most efficient analysis from sparse data. You know, every statistician in the last 100 years will say, can you get me more data? Right? Well, with eHealth research, I think we need an opposite paradigm. We need a theoretical paradigm for how to optimally throw away data. So we need to basically ignore 99.9% of the data that's out there, but picking the 0.1% is hard. And whether there are methodological theoretical tools that have yet to be developed that can enable a principled approach to that, analogous to the principled approaches to making the best possible use of sparse data, I think is an interesting open question. There will be a place for offline analysis, and a sort of a crude distinction is between, if you want to make decisions, you need real-time results. If you want to make policies, you can reflect, consider options, do things offline. Okay, now, what does the statistical modeler do with observational data? I think above all else, they buy information with assumptions. So our models are not true. They're devices that we use to answer questions, and the quality of the answers depends partly on the quality of the data, partly on the quality of thought that went into posing those questions, and partly, which is where the statistician has a very specific role to play, in the art of balancing model complexity, which improves fit to the data, and model simplicity or parsimony, which makes the model more robust for outside validation. Okay? Out of sample results are often very disappointing if you overfit a model to a given set of data. Now, a fundamental part in how we do that is by using likelihood-based inference wherever possible. There are many fewer arguments than there used to be about whether you should be Bayesian or non-Bayesian, but what all schools of statistical inference agree on is that the likelihood is the key to inference. You can't always deal with the likelihood. Sometimes it is just too messy, or the model doesn't have enough faith in it, scientific faith in it, to be used in a literal sort of sense. But generally speaking, where you can articulate a good statistical model that will answer a scientist's question, you should aim to do likelihood-based inference. Now, when you're model building, this phrase, a model should be not demonstrably inconsistent with the data, is not original. I first heard it articulated by David Cox, but he didn't claim it was original either. But it's a typically cautious statistical wording. We don't say we've got a good model for the data. We say we've got a model that isn't demonstrably bad, right? And you can argue that's just playing with words, but it's conveying the idea that we know our models are not going to be perfect, but also we know that elaborating them is going to come at a cost. We would like to incorporate underlying scientific knowledge where that's well understood, but there's no point in pretending we've got precise knowledge if we don't. And subject to those two constraints, simplicity rules in statistics. It's, to me, a very fundamental difference between mathematical modelling and statistical modelling is that statistical modelling explicitly penalises complexity, whereas mathematical modelling doesn't, because it's deductive and it presumes there is a truth out there, whereas statistical modelling knows there isn't a truth out there, and it therefore is very cautious about elaborating the models. The other analogy I like on that is with the possibly apocryphal interchange between Mozart and his imperial sponsor back in wherever it was, Salzburg, Vienna, which I think is supposed to be because the emperor couldn't play his new piece, and Mozart's response to the complaint there were too many notes was that there were only as many as there needed to be. And statistical models are like that. They only ever have as many parameters as there need to be, as opposed to any absolute number that really are there in nature, because they're all wrong. Okay, so here's an offline, incredibly simple example, and I only tell it because it's a true story. And some of you might, like me, despair on the level of numeracy in NHS senior management on this story. So, in 2009, the Health Services Journal had this rather alarming statement about increase in MRSA, which caused Edward Lee, Conservative MP, who to the best of my knowledge is not an expert in health, to say that this was threatening all those who use our healthcare system. In the same year, rather surprisingly, the Health Promotion Agency, which one would hope takes a rather more objective view of things than Conservative MPs, reported that MRSA rates had actually been falling very substantially since they'd first started being concerned about them in 2002. So it's kind of interesting that both of those statements could come out in the same year. Now, in two Lancashire hospitals that serve the area near where I live and form a single NHS trust, the data on MRSA infections, which they monitor regularly, over a period of months, stretching for 7 years plus, looked like this. Now, you may laugh at this, and in fact you're right to laugh, but I followed it through just to make a point. Where the question mark is pointing down, the head of the path lab had actually got a call from the chief exec's PA saying, the chief exec wants to see you. Can you explain the increase in MRSA incidence? What should we be doing about it? Well, every case of MRSA is one too many, but signal and noise happen in things like acquiring infections in hospital. So the question that would arise in the statistician's mind is, well, yes, there is a lot of noise in those data, but if we simply say it's all noise, perhaps we're being a little bit cavalier. Let's actually analyse those data and see what's going on. And I would guess, you can guess roughly what the answer is, but we'll just follow through the details anyway. It's always nice to plot data like that as cumulative incidence rather than absolute incidence. We've actually got the dates of each case, so we don't need to group them into monthly counts. We just plot them cumulatively, or weekly counts or anything else. And you can see there pretty clearly that the black solid line has a convexity to it. And what that means is that the rate is falling in line with the Health Protection Agency's findings. The dashed line is pretty much a line, pretty much linear, and that means that in the other hospital, which is much smaller, which is why it's got fewer cases, there's been no particular improvement. On the other hand, you can see it's also shallower than the other lines, so there was less room for improvement because they were already doing better in terms of rate per 100,000 patients. Okay, well, let's dig a little bit deeper. And if we really did just have noise, right, then what we'd expect to see is a Poisson process. The Poisson process is a completely random pattern of events in time. This diagram is supposed to show, although the confidence intervals are practically invisible on the screen, for which I apologise, but those smooth curves on the two plots are the fitted trends, okay, over the period of the data, and they're going materially downwards in the big hospital, downwards but not significantly so in the smaller hospital. So that's consistent. That's just formalising what you saw in that picture. There is an unequivocally significant drop in incidence in the large hospital over the time period. There's a non-significant small drop in the smaller hospital. But the reason why I wanted to fit those trends was because I wanted to ask what the residuals about that trend looked like. And if the residuals about that trend just look like a Poisson process, then what that's saying is that anything else that you may or may not see in that pattern is just noise. So looking back at this raw data, which is what was in front of the, well, I don't suppose the graph was in front of the CEO's desk, it's probably just an Excel spreadsheet. But what you see as a downward trend is real. But any sense of, oh, having a bad time, now that's just noise, statistically speaking. So it doesn't mean you don't worry about every individual case, that's a different issue. But in terms of whether the hospital systemically is having a problem, the answer is no. There's a very good fit. Again, I apologise for the faint lines, but the solid and dashed lines here are the theoretical and fitted cumulative residual plots. These are point process residuals. I'm not going to define them, but as you'd expect, a well-fitting model has the empirical solid curve close to the theoretical dashed curve, and they look pretty good to me. Also, if you look at the intervals between successive cases, you find that they're uncorrelated, so you don't get clusters of short intervals followed by spaces. So what you want to do in this case, in other words, is if you think that these cases need to be reduced, you want to get the trend down, but what you've not got are outbreaks that are because of periodic slackness on the part of individuals or whatever. Okay, so that's just a simple offline analysis using simple modelling tools to actually distinguish whether there's something actually worth following up here. And the statistical answer is no. If you want to do something about this and you want to get the long-term average down, you've got to think long-term average policies. But jumping in because this month we've got more cases than we thought is a complete waste of time. It's just following the noise. And you don't improve quality of care by following noise. You improve it by following the signal. Okay, any questions on that? You'll have time at the end as well. But okay, so now let's look at something which is moving more towards real time and certainly a much more substantial data set and a very real problem, which is dealing with renal failure in the UK. The site that I got these data off seems not to have been updated since 2008, and I'm surprised that I've been unable to find a more up-to-date slide. That's probably just haven't looked hard enough. But certainly over the early parts of this century, UK mortality attributed to renal failure was increasing quite a lot. And there are a number of reasons for that, one of which is the shortage of organs for transplantation, one of which is the changes in lifestyle that mean people are more prone to diabetes, and diabetes is a causal factor for renal failure. But it's a big problem, that's the point. It's easy to diagnose kidney failure. You measure serum creatinine in the blood, you convert that by a quantitatively dubious but qualitatively very sensible formula into something called estimated glomerular filtration rate, which is the function that the kidney is actually doing. And so it ought to be easy to actually find out when people's kidneys are failing. The reason in practice it isn't is that kidney failure can be asymptomatic for many years, and unless you're actively monitoring for it and doing the right blood tests, there's no reason to suppose there's anything wrong with somebody's kidneys until they're down to about 10 or 20% of normal function. And by that time, they suddenly feel ill and they've been told, your kidneys have failed. Okay, well, can we do better, right? So, well, firstly, why do we want to do better? We want to do better because most forms of kidney disease are irreversible. Some are, but most are not. But also, most can have their rate of progression slowed by aggressive control of blood pressure. So if you know that somebody's at risk of kidney failure, you really look at their blood pressure, you give them antihypertensives, and you can slow the rate of decline. And what that means is that it is actually rather important to be able to do that, because renal replacement therapy in the UK is not actually easy to get. There is more demand for it than there is supply. The supply and demand imbalance is particularly acute in transplantation, but even in dialysis. Even when you've been diagnosed with end-stage renal failure, you might think you'd be on dialysis within 24 hours. It's not true. Certainly not all around the country. If it's true where you live, then that's great. And transplants are really great things, because if you compare the 5-year survival rates, admittedly marginalised over all sorts of other risk factors, you can see that with dialysis, it keeps you alive for a while, but the long-term prognosis is superficially not good. I mean, frankly, because a lot of people get kidney failure in their old age, a lot of this may be dying for reasons unconnected with kidney failure. But the transplant prognosis is much, much better, and the quality of life on transplant is infinitely better than the quality of life on dialysis. Okay, so what is this getting around to? Well, it's getting around to the fact that, having established from clinical experts that early diagnosis can slow rates of progression, the question was put to me by the renal department at the big teaching hospital in Salford, Greater Manchester, the Royal Salford. How could we use routinely collected primary care data of people at risk to monitor the decline in renal function and actually identify at the earliest possible stage that they needed to be referred to secondary care? And so I asked the question, well, when would you want somebody referred to secondary care? And after a bit of debate, they said, if we knew that somebody was losing 5% of kidney function per year, we'd want them referred to secondary care. Okay? Now, you could say, fine, all you have to do is take 2 blood tests, take the difference between the two, divide by the time interval, and is the answer bigger than 0.05? And of course, that's just analysing the noise. And what you want to do, as in my simple first example, is separate the signal from the noise, because you want the signal to be decaying by more than 5% of the year, of kidney function per year. And the assay for serum creatinine, which is what you calculate eGFR from, is noisy. Now, we're in the fantastic position in Salford, which is particularly pertinent to the eHealth agenda, that all of the primary and secondary care data from Salford City goes to a single server overnight and is accessible to bona fide researchers who have to go through a formal application procedure, but compared to the hurdles of going on a project-by-project basis to medical ethics, it's really very easy to access these data. And every clinical event is lodged there. And so for this project, we extracted data on somewhere shy of 200,000 patients, within which, in particular, there was a cohort of primary care patients. So these are patients who had never been referred to secondary care for their renal conditions, but they were, because of their comorbidities and or other risk factors, they were judged to be at risk of kidney failure. And if you look at the records on these people, they've all had blood tests. Some of them have had a remarkably large number of blood tests, because when you suffer acute illness, if any of you have been in hospital, the one thing they do all the time is stick needles in your arm and take blood. Okay? Some of them have had rather few, but that's a big, big set of data. And what we want is to look at some simple covariates that we can be sure we can get measured alongside their eGFR. And here we've got age, sex, diabetes, yes, no, and albuminuria, yes, no. And say, what do those time sequences actually look like? And could we, therefore, build a predictive model that we could run in real time to identify the patients who ought to be transferred to secondary care? Now, if you look at the data cross-sectionally, in other words, you just do a scatter plot of age against eGFR, it looks a horrible mess, as scatter plots of big data sets usually do, but there is an obvious trend in there, okay? And it's kind of at the rate of 1 or 2% of kidney loss per year, which is probably what a lot of you are suffering without realising it. But don't worry, because unless you are suffering a lot more than that, your kidneys will last you out and other things will get you first. If you look longitudinally at the data, that means focusing on the trajectories on individual patients. You can see the variation that we need to deal with, because some people are ostensibly getting better over time, and indeed eGFR itself is a proxy for the true state of your kidney health. And if you go on a fitness regime and change your muscle mass, you'll change your serum creatinine. And the formula for converting serum creatinine to eGFR is not perfect. So there are a lot of extraneous factors here which mean that some people are genuinely getting better on eGFR. We just have to live with that. But the ones we really want to identify are the ones like this person who's clearly on a downward progression. But there's a lot of data in there, and the question is, could we have identified that person as being at risk earlier if we had done something a bit cleverer, not a lot cleverer, a bit cleverer than just plotting their data. Okay, so here's a clearer picture of some sample traces from individuals, and you can see there's a lot of variation between individuals at a given age. There's a lot of variation over time. There are some apparently quite convincing trends which suddenly get reversed. It's really very messy data. But that's what currently clinicians have to make decisions on, and they probably, as I said earlier, don't even have the plots. They just have the piece of paper from the lab. It's not silly to just fit straight lines to individual people's records and calculate the slope. The trouble is, if you do that from very few points, they're obviously very unstable. And I've chosen here examples where we've got a reasonable amount of data. But all we're trying to do is do something, say, a little bit more sophisticated than that, which we can do in real time and update as new data come in. So what we do is we build a model. And the model is really just a regression model, but it recognizes that there are variations happening in these data which we can't capture in the covariates that we've got measured. So we model on a log scale, because that seems to be the right thing to do. I'm not going through any of the technical details here. And we build a regression model in which we include both fixed effects, which are the covariates, and random effects. And the random effects have two components. Based on what we see in this slide, we posit that there is a random level that each person has, having corrected for their covariates, but there's also a random slope, and that random slope is not constant. You know, there are phases when somebody's coming down quite hard, and then something happens to make them go back up. Now, I don't know what that something was, and I'm not going to be able to find out. But we need to capture those phenomena in the model. So what we do is we build a stochastic process, C of t, which is the integral of a random walk, and it's that random walk b that is the slope. So it's basically a dynamic linear regression with a subject-specific intercept, right, and a randomly but smoothly varying slope over time. And you then have some parameters that you have to estimate, so you maximize the likelihood, or if you're Bayesian, you put a prior on and integrate the likelihood. It doesn't make any difference because the data swamp any reasonable prior. And you get this picture. And you can see that what I've done is really just smooth out the data by something that wants to be linear if the data don't tell it otherwise, but will respond cautiously to changes in the empirical slope. And what that model is doing is balancing. It's not ignoring the changes in behavior of the data, but it's skeptical of them because it's estimated the signal-to-noise ratio. And so that is now, if you like, our point estimate of the time-varying slope for each of those 4 patients. But what's more important, I think, is that because this is all based on likelihood analysis of a probability model, we can compute probabilities that we're interested in. And in particular, we can compute the rate of progression at time t as a function of the data observed up to time t. And we can do more than just compute its value, we can compute its distribution. So the result of fitting this model to data is that at any time t and for any patient I, we get a distribution of what we think their current slope is. And we can turn from that distribution, we can calculate the probability that that patient meets the clinician's criterion of referral to secondary care, namely loss of at least 5% per year. So we produce pictures like this, of which you only need to look at the top left and bottom right. The others are just checking that the algorithms have converged. And top left is a typically noisy profile in which at the end of the series it's pretty clear that that person has got a long-term decline in their kidney function, but it's less clear early in the series. So what we do is we start off with a 50-50 call. You have to start somewhere, and 50-50 call is probably not quite right for these data. But what happens is, as the data come in, initially the model is not terribly impressed because it doesn't have much information. But as the series gets longer, it begins to feel happier that this person really does have a decreasing trend, and it reaches a probability of about 0.7 or a bit more that that person's trend, underlying trend at that time, remember the trend is changing over time, is, we don't know what it is, but we're 70% sure it's less than minus 0.05. In other words, that person should be referred to secondary care with probability 0.7. It's not a sure thing. For data like that, the predictor probably will never go to 1 because of all the noise in the data. But you know, it certainly responds, and it responds cautiously but honestly to the noise signal balance in the data. Now, what a clinician should do about that is none of my business. And one of the things I like about this example is that this person is 84 years old, and for all I know may have other frailties that would mean that major surgery would be inadvisable. But the point is that that is taking what is a noisy record, which I would claim is actually very hard to interpret, into something that objectively says, you've told me the clinical criterion you're interested in, I'm telling you this patient has a 70% probability of meeting that criterion. You now have to make a clinical decision taking into account other factors, not least your skill and judgment as a clinician. Okay, this is an example that just shows the algorithm works if you really push it, because this is another patient who plausibly has given a bad data point, right? I've been called into hospital more than once in my life through one data point like that. Okay, the model is totally unimpressed, right? But it was wise to take another one, and indeed that was an outlier. Here we've got a catastrophic fall, right? And the model responds very quickly and says, I'm pretty sure this person's losing more than 5% of kidney function a year. What happened there, I don't know, but strongly suspect this person had an accident, and they had what they were suffering from was acute kidney failure, which is remediable. They probably have bleeding kidneys. And after an acute injury, you can sometimes get a catastrophic but reversible fall in kidney function, whereas chronic kidney disease is mostly irreversible. And again, there's a context there that I'm not privy to. But it may be that this person was already in hospital being treated for trauma, and the kidney damage was a side effect, and it proved reversible, and you can see that they got back up to there. Now, interestingly, this also illustrates a problem I'm not talking about today, but we are now working on with the Salford Royal people, which is, they call these things acute kidney injuries. They're defined by what they do to the kidneys rather than a certain class of events, but they have an open research question as to whether typically when you have one of these acute kidney injuries you actually get back to where you were before, or you suffer a long-term consequence. This person, on the face of it, may have suffered a long-term reduction in their kidney function through that traumatic injury. I don't know, but statistics can help us find out. Okay. That's the end of the second case study. Again, any quick questions of clarification, or we'll come back at the end for general ones. Now, revealing my colours, one of the few good things the UK government has done in its tenure is to move towards more open data. And in particular, anybody, including any of you, can download from the web the complete prescribing patterns by NHS doctors on a monthly basis. Rather ironically, in view of current political developments, I believe you can only do that for England and Wales, but you may have a different system in Scotland, which is even better, like most of your social services. But it's an extremely useful tool if you want to actually quickly scan through surprising features in the geographical distribution of what NHS doctors are actually up to. Because you can link these data to a GP database, which will tell you where the GPs are, what their capitation lists are, stratified by sex and age group. You can link it to the national census, and that will give you socio-demographic information on who actually lives near those practices. Now, that doesn't mean they use them, but broadly speaking, people use GPs near to where they live. So there's quite a lot of potential there for asking interesting questions and using these data to get answers. And as a very simple first pass through these data, you can simply say, we've got a location, we know how much they spend a month, we know how many patients they've got on their register, so we can have a crude prescribing rate, which is the ratio of those two things. It's not quite fair because a lot of drugs, as you know, have different makes which cost slightly different, and some people might want the pink ones or the blue ones or the sugary ones. But roughly speaking, that's our proxy for the volume, the prescribing rate. And what we then do is we argue that partly because we want to smooth out the noise in the data, and partly because we don't know exactly where people live who go to a particular GP, we surround each practice by a circle whose radius is chosen so that we include GPs with a total capitation of some number, which the bigger that number is, the smoother the results will be. So instead of doing it on a per practice basis, we're doing it on a per circle basis of practices that total capitation. And I think from memory we used something like 8,000 or 10,000 for M. And then what we basically do is we use the simple device of a kernel smoother with weights which vary, okay, according to how far each practice is from the centre of that circle, and that gives us a kind of continuously moving spatial average of prescribing rates in the locality of each GP. And if you do that for the frontline medication for diabetes in England, you get this map. And you get a lot of variation. The numbers are not clear, but the dark blue is 2 pence per person on average, and the dark red is 30 pence per person on average. So there's a 15-fold ratio in prescribing rates. Now, I am not competent to know whether that's reasonable or not. But what I can do is say, well, where are the really statistically unusual things on that map? Or is it just, like my very first example, random variation about an underlying mean of about 15 pence a patient? Well, if you just zoom in to places you're interested in, you can see in London it sure as hell isn't random. There is a very obvious difference between what goes on in, roughly speaking, central London and what goes on in the periphery, particularly the northern periphery. And many of you will know that these South Asian minority populations of London live more in the north, and in particular the northwest, around places like Ealing and Southall. And also, ethnicity is a risk factor for diabetes. So there's a very clear geographical pattern there that may or may not, because you have to know about London to answer the question, be a reasonable reflection of difference in risk factors, which you could then model through the census or whatever. But Sheffield, similarly, you can see these local partitions, and if you know about Sheffield, you can speculate on why the blues are to the west and the reds are to the right, other than the football colours. In order to actually pick out what I think are, I like the word anomaly, because I don't like the word cluster, because a cluster implies some sort of mechanism that you think you understand, whereas an anomaly is something that clearly you don't understand. And I think that's the right, appropriately humble way for a statistician to express their results. Okay, so the working hypothesis of uniform prescribing rates would tell you what you expect these smoothed estimates to look like, and we do a kind of a significance test, but it's a kind of a significance test in which we choose a ratio C, and we say, for example, if C equals 4, which it is on my next map, what's the probability, okay, that the local estimate is more than 4 times the overall average? Okay, so it's sort of like testing a null hypothesis, a one-sided null hypothesis, that the local rate is less than or equal to 4 times the national average. And on the other way, it's like saying, testing a hypothesis that the local rate is at least a quarter of the national average. I mean, Dennis Lindley would turn in his grave with this kind of words, but it's as a kind of way of, because if you just do significance testing, everything's significant, because things vary for all sorts of good reasons, and we've got huge amounts of data. So there's no point in doing standard significance tests, but these kind of shifted significance tests seem to me to be a reasonable tool for filtering out the data. So if you redraw the maps on that scale and look at attention deficit hyperactivity disorder, which has huge variations in how much money people spend on it, and you hone in on somewhere you actually know, which in my case is Liverpool in the northwest of England. Oops. There you have it. You have the city of Liverpool full of blue, which is low prescribing rates for ADHD, and you have the Wirral, which is the peninsula between the Mersey and the Dee, full of red. Now, I don't know how well you know Merseyside, but there's a lot of poverty in central Liverpool, and there's a lot of affluence on the Wirral. Okay, so I'll leave you to speculate on what causes ADHD, or rather, what causes people to prescribe for ADHD. And again, I'm no expert, but it seems to me that that is shouting at you so loudly. Why hadn't anybody noticed it before? And it was on Radio 4 just a couple of months ago, someone saying, why are people prescribing ADHD in Wales as though they just discovered it? Well, the information's been there all the time. And the point is, you know, unless you've got a lot of time, if you look at maps like that, you just haven't got time to hone in on everything. So it's nice to have that filter that really says, no, where are the really, oh, yes, there are only 2 or 3 of them. And in fact, oh no, that's a road marking. I thought maybe the North Wales one showed up as well. Ah, no, it didn't, because this is just English data. We're just analysing in England. Had we analysed Wales, presumably we would have found that as well. Never mind. A second example of using the prescribing data to sort of look at what health authorities are up to is if you look at the PCT level, these are the English PCTs, and I'm going to look at the northeast of England, of which again I know something. If you look in the northeast here, that's the top left plot, something rather obvious hits you, okay, which is that within the northeast, most things look like they look everywhere else, except for this one thing here. So if we just expand that one, I mean, again, the writing's criminally small, I forgive you, but that's actually rural Northumberland. And for some reason, the GPs in rural Northumberland are doing a lot more influenza vaccinations than any of the other areas of Northumberland. This is one winter's record. I haven't actually looked at the more recent one, but we should. And what's interesting is that there's a notional count of who ought to get a flu vaccine in each area, you know, based on whether they're old or have risk factors or whatever. And the scaling here, which again you can't read, this is a really good lecture in bad graphical presentation, is there. So actually, all these guys, they may take a few months to get there, but they get to just about where the government says they should. So this authority is actually giving flu jabs to 2 or 3 times, certainly at least about twice as many people as the government guidelines say should receive them. Now again, whether that's good or bad, I'm not qualified to judge, but it's very different, and it shows out immediately from looking at these kind of data. So that's the outlier, rural Northumberland. And I don't do the computing stuff, despite Claudia's kind introduction. I have an extremely able colleague called Barry Rowlingson who builds all the systems for these applications, and this is just indicating the way you need to have in 4 data repositories, all of which are readily available, and you have to link them to get the information you need to draw these maps. Okay, last case study, gastro-intestinal disease. When I first gave this talk, which is more than a year ago, this was an old problem, and it's become a new problem again because we've got a sudden burst of injection of funds from the impetus of the FAR and a grant from Wellcome. So we're reviving this problem. So I feel I can talk about it again. There's a lot of gastrointestinal disease in the UK. A lot of it is presumed to be foodborne. It's also presumed that the true burden of disease is much, much larger than the number of reported cases. And my colleagues in Liverpool, you know about these diseases and have a view that these are important public health problems. What we first did in about 1999-2000 was built a real-time surveillance system based on the then new NHS Direct. It may have been 2000, I can't remember. Whenever NHS started, the project started just before NHS Direct came online, and NHS Direct was its salvation because NHS Direct has a very strong administrative infrastructure, which means that anybody who phones NHS Direct, you can be sure that the time and date will have been recorded. We only use the date, and their postcode will have been recorded, and that you can convert into a location. So minimally, you know when they called and where they lived, and finally they have to log a code for the primary reason for the call. And if the code was sickness and or diarrhea, we called that a case, a potential case. So this is not very non-specific first pass surveillance. And if you look at those data empirically, the pattern is really very sporadic, but you do occasionally get apparent clusters, I said I didn't like that word, which is why I've put it in inverted commas, of cases that might reflect some public health event that you actually want to do something about. These things are pretty slender in the following sense. This is the county of Hampshire, and what I'm going to do is I'm going to run an animation which in real time shows you a moving window of 5 days worth of cases. So you can see that the cases are mainly concentrated, surprisingly, where people live. And the question is, what happens over time to that geographical distribution of cases? And what happens is that it begins to hurt your eyes after a minute or two, because it really just looks completely lacking in any kind of pattern, right? And that's actually the kind of pattern for which statistical modelling is particularly useful, because I think this defeats the capacity of just the human eye to spot an unusual concentration. Whereas when you very occasionally see these patches of red appearing on the map, like that, that's where, according to a model that I'll describe in a couple of slides, there's a very high predictive probability that the local rate there and then was at least twice what it should have been for that time of year in that place, adjusting for its population. And these maps were actually running in about 2002 on the public health laboratory system in Southampton, and every morning there was a daily update based on the latest cases. But it's subtle. The clustering isn't terribly strong. And just to emphasize what I mean by subtle, although this is not something I want to talk about in any detail, there's a similar animation here of the foot and mouth epidemic in Cumbria in 2001. And you can see that although notionally it's just, again, points appearing on a map, it's completely different. You can see very clearly what's going on with foot and mouth. It's being spread through an infectious agent, which we know is infected droplets exhaled by infected animals. And you know, the epidemic modelers can have a field day with data like this. They can build differential equation models, they can do all sorts of things, because the process has really got a very strong signal to it. But the kind of signals you get from human disease are always weaker because human beings don't behave as they're told, whereas animals, unfortunately, have no choice. So they have to. So that's just a very, that's just to emphasize that this pattern doesn't obviously have much of a signal going for it. Okay? So if we go back to the business of the day. What's our model? Our model here, because we don't really understand the science, because the science here is as much social as natural, right? I mean, what causes people to call NHS to raid? I don't know. It's a million things I can't measure on them, right? So what we do is we say, well, what we see is what we expect times what we don't expect. It's a bit like weather. Weather is what you get and climate is what you expect, right? So what we expect is for certain places to make more use of NHS Direct, and we expect certain times of year to make more calls to NHS Direct, because the risk of disease varies seasonally. If foodborne disease typically has peaks in the early summer in this country, and sometimes, as you'll see shortly, sometimes it has a kind of double peak, which apparently intrigues people. The idea then is to say that when I say unexpected, I have in my mind a stochastic process, because to me probability is simply formalizing uncertainty, or if you want to be unkind, it's formalizing ignorance. We don't know why what we expect doesn't happen, so we model it stochastically. But this is a stochastic process which recognizes that things close apart in space are more similar than things far apart, and things close apart in time are more similar than things far apart in time. But again, what we do, and it's really a spatio-temporal version of the renal monitoring problem, is we use the historic data that we've got, which for this project was 3,000 cases over 3 years in Hampshire, to build the model for lambda naught, the model for R, and then we run it, and we calculate these predictive probabilities of R being greater than 2, 4, 6, 8, whatever the clinician wants, and we map them. Okay, so that's just repeating the previous slide but with a bit more notation. And the important part of this notation is that if all you've got is a single data set of this process, you can't unambiguously separate out what you expect from what you get. In classical statistics, what you expect is what's reproducible on replication. What you get is random variation about that. We only have one realization. So we can't use the data to tell us what's expected and what's unexpected. So we make a structural assumption that what we expect is different places to show different calling rates, and we expect different times to show different calling rates, but we think those things should operate independently. In other words, there should be a general rise in summer, not a localized rise. Wouldn't be true if we're doing this globally, because different weather patterns would have different effects in different places, but Hampshire is a pretty small place. And on that basis, anything that doesn't separate into a product of purely space and purely time, we call it stochastic. And that's what we're trying to predict. It's that term that we're saying, is that term bigger than 2, bigger than 4, bigger than 8? And the numbers 2, 4, and 8 are the numbers that would get a public health person to get out of bed and worry about what was happening. So it's not, again, not my choice, it's the expert's choice. Right, and so what we've got here is a model for a Poisson process of the kind I fitted right at the beginning of the talk to that simple problem in the Lancashire hospitals, except that now it's a spatio-temporal process, and we don't know what the correct model is for the intensity function, so we model it stochastically. We take out what we expect and are not interested in, and we look at what's left. That's basically, remember I was using adaptive kernel smoothing in the prescribing data. This is the same idea. This is simply a smoothed map of where people, on average over time, use NHS Direct. It's similar to, but not equal to, a population map, because different demographics have differential use of NHS Direct. So you can't just use population denominators. Arguably, you could use age, sex, stratified population denominators, but for better or for worse, what we chose to do was to use a smoothed version of the time-averaged pattern of calls. And there's our model for what we expect. A peak reproduced in 2 successive years, and a rising trend which we're almost certain was basically telling us about the increased uptake of what was then a new service rather than CAMPI. So again, in terms of, even although that's artificial, it's right to put it in the model because you want to eliminate it because it's artificial, right? What we really want to do is say when are the big residuals about this model. Okay, if you look at the covariance structure of the stochastic part, the algebraic form of these functions is unimportant. What it's trying to convey is that on the left, there is statistical evidence of correlation in the sense that rates are similar when they're close in space, up to a distance of about 1 kilometre or so. And on the right, rates are similar if they're close in time, up to a distance of about 5 days. And remember, this is acute gastrointestinal illness. So there will be varying latencies between when people get infected and when they call NHS Direct. But days rather than weeks is the right kind of order of magnitude. So that's encouraging. And then we basically just turn the handle. We, which is the royal we, I mean me, it means one of my much younger colleagues, writes an MCMC algorithm so that we can generate samples from this underlying unknown part of the process, conditional on the data we've seen, and we can map the probabilities that that ratio of what we get to what we expect exceeds whatever threshold the clinician is actually interested in. And so that was in case the animation didn't work. That's a static map of the 6th of March 2003 with apparently 3 anomalies, here, here and here, using a threshold of 2. And if you tamp up the threshold to 4 or 8, you can see that they largely disappear. And indeed, if there is something that's actually of public health significance, you'd expect really quite a high threshold because at any 1 pixel in this map, the expected number of cases is a lot less than 1. Right? So as soon as you start getting multiple cases, you're into ratios that are really quite large. And that's why it's a bad idea to try to estimate risk, because it'll just be very spiky. It's much better to say, I'm not interested in estimating risk, I just want to know if it's sufficiently high to be a public health concern. The way we presented this to the users all those years ago was through a web page like this, which was being updated invisibly every day, but you could look back if you wished. It's really a demonstration site at different dates, and you could say, okay, that's with an exceedance of 2, that's an exceedance of 4, that's an exceedance of 8, yeah. What will happen tomorrow, I wonder? Oh, not a lot. Oh, there's something there that just might be, and you can play around with it. But that was the basic idea. And what we've now got is, to say, a new slug of money to build a new version of this system in which we're hoping to have something a little bit more dynamic. But the principle is the same, that we'll get data feed of cases, we'll run the model, we'll report back anomalies. That the exciting difference from a public health point of view is that we're now working with people who understand the diseases, and our system will now trigger follow-up sampling, which is focused and which uses high throughput methods to get quick diagnostic answers of cases in those potentially anomalous areas. So rather than the scattergun approach of just taking samples wherever you can find them, it'll focus the sampling in proactively on areas where there seems to be potentially a problem. And some of those will be false alarms, I'm well aware of that. But the idea again is it's a kind of first-line filter that's followed up with work by people who actually know about the science. Okay, so that's about it really. To me as a statistician, there are methodological challenges here, of which the obvious one is we need to combine information from multiple data sets which are not all collected on the same spatial or temporal units. And that's a long-standing problem in geography called the modifiable aerial unit problem. But I think with modern computational tools, we can get a more principled statistical solution based on the likelihood for the model, and several of my younger colleagues in Lancaster are working on that as we speak. Incomplete coverage is always a problem because the incompleteness may be biased, and so having offline projects that can actually understand why particular subsets of the population do or do not access particular sorts of healthcare seems to me to be essential to interpret these kind of automatic results correctly. having biased results is bad, but it's not so bad if you know why they're biased, because you can make an informed decision about what to do about them, and that's where you need something much more multidisciplinary. It's really all about, public understanding, psychology, sociology, economics, transport access, all sorts of things come into the population there. A long-standing problem in epidemiology, which people usually ignore because they don't know what to do about it, is the substantive relevance of residential locations. I mean, we tend in spatial epi almost always to codify people by where they live, but people move about. And there are beginning to be some interesting projects where we use very simple modern technology like mobile phones, so that the data consists of people's tracks through exposure space rather than just points. And I think it's interesting to know how you would model and analyse data where each person's data tells you what they did over the last 24 hours and relate that to something like an air pollution surface or whatever. A lot of my colleagues in the physical sciences tell me they've got data on climate, and they haven't got any such thing. What they've got are models that produce pseudo-data, and I think understanding the difference between model outputs and measured data has some statistical implications that we need to think through. And again, this is not statistical, but I think it's absolutely vital. There are two things to do about uncertainty. One is to actually pretend it's not there, which people like, and the other is to work very hard at communicating it, which is what you should do. But communicating uncertainty is not necessarily something that statisticians are particularly good at. And again, I think some of the social sciences have something to offer in terms of effective and ineffective ways of communicating uncertainty to intelligent lay people. The one that really I'm trying to work on at the moment is the notion of data synthesis, in which we have, the approach would be to say that the phenomena we're interested in are operating in a spatio-temporal continuum. The discreteness of space and time comes artificially because of political or economic or technological constraints. But rather than modelling in that artificial space, you should build your models in the natural space. And then the challenge for statisticians, which is really this modifiable areal unit problem again, is to derive likelihood-based methods of inference for the data that you've got, and in particular for combining multiple data sources. And a lot of what I think we're doing in statistics with data of this kind should really switch not only from testing, which is easy to criticise, but also from estimation, because mostly it's about prediction. It's prediction to prompt action, prediction to prompt thought, prediction to prompt reflection on policy, or possibly to propose an objective study of a controlled kind. But it's not really about estimating parameters, and the parameters are just devices that allow you to draw these predictive maps. So to me, the real challenge is to communicate the idea of predictive probability to health professionals and decision makers. Okay, lots to do. Fantastically interesting, and as I say, I think gold standard, the RCT may be a gold standard in some people's eyes, but I don't think it's going to cut it for eHealth. And I actually think, rather more heretically, that sometimes the obsession with RCTs mean that you settle for answering a rather less interesting question because you know you can answer it well, rather than following Tukey's advice, which is that it's better to have an approximate answer to the right question than a precise answer to the wrong question. Okay, all of this is either published or about to be published, and if anybody does want to follow it up, I hope those references are useful, and happy to take questions. Thank you for your attention.
Thank you. That was an excellent presentation and very well rounded.